Hello, hope everyone is studying well and enjoying life. This small module is to do with questions with respect to parametric equations, and there are a number of questions. If you find them in past papers to do with x equals a function of t, y equals a function of t, and then you need to find derivatives and find Cartesian equations with such types of equations. So we're going to just look at one in particular in this particular module, and this question here shows two equations, x equals sine of t and y equals sine of t plus pi over 6. Keep in mind that t is somewhere between negative pi and 2 and pi and 2. In terms of radians, that's to negative pi and 2 to positive pi and 2. That means quadrant 1 and quadrant 2. So keep that in mind later. That comes in handy when we're dealing with sine and when we're dealing with cos of that particular value. So cos will always be positive no matter what, and sine of t will be positive and negative. So it is possible for sine to be a negative value. So x equals sine of t and y equals sine of t plus pi over 6. So we're asked to find an equation of the tangent to the curve at the point where t equals pi over 6. Well, we need to know the gradient and a point, and we can find the gradient by first of all finding dy dx, and we will use a combination of dy dt and multiply that by dt dx, which is the reciprocal of dx dt. So dx dt happens to be the derivative of sine x, which is cos t, the derivative of sine t, which is cos t. And the derivative of this equation, dy dt, the derivative of sine is cos t, and there's no power, there's no coefficient here, so we don't have to multiply by anything apart from 1. And therefore, we can now say that dy dx, to find the gradient of our tangent, will be dy dt times dt dx. So dy dt is cos of t plus pi over 6. And dt dx is the reciprocal of dx dt. So that would be cos of t. Now, let's just find the gradient, dy dx, at t equals pi over 6. You substitute pi over 6. So that would be cos of pi over 6 plus pi over 6, which is pi over 3. And 1 over cos of pi over 6. Cos of pi over 3 is the same as sine of pi over 6, which is a half. And the reciprocal cos of pi over 6 is root 3 over 2, and reciprocate that, 2 over root 3. So we've got cancel, so we've got 1 over root 3. Therefore, the gradient of our tangent is 1 over root 3. We know the gradient. All we need now is a point. Now, x, when t is pi over 6, is sine of pi over 6, which is sine, which is a half. And the y value is sine of pi over 6 plus pi over 6, substituting pi over 6. Sine of pi over 3, which is root 3 over 2. So at the point a half root 3 over 2 with a gradient of 1 over root 3, we will get our equation of the tangent. Now let's just use y minus, I like this equation, equals mx minus x1. I'm not sure if you use the same equation. But y minus root 3 over 2 equals m x minus x1, which is a half. Simplifying this equation, we could multiply this root 3 across that side, so we get root 3y and root 3 times root 3 over 2. X minus a half. I could double everything. Let's just make that 3. I could, well, let's just take that root 3y, make that minus 3 over 2, put that over here as plus 3 over 2. And that makes plus 1, doesn't it? Therefore, root 3y equals x plus 1. Right. So that is an equation of the curve, and now we have to show that the Cartesian equation of the curve is. Now we've got to show that the Cartesian equation is y equals some function of x. Now, y equals sine a plus b. You know this rule here, I'll put it up here. Sine of a plus b. Remember this rule? Sine a cos b plus cos a sine b. I think that's the formula sheet. Therefore, sine of t plus pi over 6, which is what y equals, is sine of t cos pi over 6 plus cos of t sine pi over 6. Cos of pi over 6 is root 3 over 2. So root 3 sine 2 over 2. Sine of pi over 6 is a half of 2. And that's what y equals. Y equals sine t plus, therefore y equals. Now we just have to get x here. Now notice x is sine t. So we could straight away replace that with x. So y equals root 3 over 2x. And we've got this one here. We've got to be happy about that. Plus, now we've got this half, but we've got to now look at changing cos of t. Now this is where if I was to use it in terms of t, remember this Pythagoras Theorem, cos squared t is 1 minus sine squared t, and cos t equals plus or minus the square root of 1 minus sine squared t. Sine t is x, so we could put an x here, plus or minus 1 minus x squared. Now remember before, we mentioned that cos of t is a positive number because it's quadrant 1 and quadrant 2, and cos is positive in quadrant 1, cos is positive in quadrant 2, therefore cos cannot be the negative. So down here, cos can't be the negative part. So cos can only be positive, not negative. We could replace cos of t with, yes, we're almost finished, half square root of 1 minus x squared. And there we go. For both parts, although it's split, it's presented up to the right, it's exactly in the best position. Alright, here is a question on parametric equations. Just looking at our solutions, we said the equation of the tangent was root 3y equals x plus 1. Let's have a look at what the equation said. Well, they came up with 1 over root 3 as the gradient, That's what we have. They came up with an x-coordinate of a half root 3 over 2. That's what we said. And it almost looks the same as our equation. They've written it slightly different, but if you have a look at, if you times everything by 3, you would get 3x equals root 3x plus root 3. And if you factorize root 3 out, plus 1, and that's 3 over root 3, 3 over root 3y equals x plus 1, and 3 divided by root 3 is root 3, root 3y equals x plus 1. I don't think we would be penalised for answering it in this shape. It's got here t equals that or t equals that. I struggle to see if we would do them not. It would be fine. Part 2, yes, they've split this up into sine cos plus cos sine, and then they've replaced cos t with square root of 1 minus x squared. Therefore, we've got the same solution. Wonderful. All right. Well, that's a very small revision point with parametric equations. I wish you all the best with your study. Find other equations that look like this, and probably a good idea to try it now. Let us know of any successes that you have, and stay happy.